Okay, let's start. So, so last time we almost finished all of the chapter 5 to 6, and we are going to wrap it up. So last time we learned the hydroboration, oxidation, and reinforced the your understanding of the mechanism of that. And we also learned some the concepts of oxidation and reduction, and also the hydrogenation using platinum and platinum carbon catalyst. And also we started dihydroxylation, epoxidation, and almost finished all the analysis. Okay, so again, there are some dates we need to remember. And midterm 1, October 9th. And I will give you a full detail about the exam on next Monday, so next Tuesday, okay? And I have already uploaded the midterm 1 of 2016. So this is an exam administered by Professor Lee. And I also included the examination. So the file is a PowerPoint. So you can see the answers and the questions and the explanations of these problems. All right. And also, a lot of you still don't know that there is some problems and there are some practice problems for each chapters on Moodle. So, and I have looked through these problems, and these are really good ones. So it's really good for you to practice, and there are a lot of them. So, and I would say if you finish all of them, you are going to be pretty good at all the contents we have taught. Okay, so if you can see, it's on the Moodle and in the assignment and exercise part, and you can see here. Okay, we have practice problems for stereochemistry, and we have practice problems for chapter 5 to 6 and chapter 7. You can see if you open it. So they have problems, and at the end of each problems, there are the answers. Okay, so basically you can teach yourself solving these problems, and you can also have the answer. Okay, so really good ones. There are like tens of them, I think. Okay, 52. That's a lot. All right. So if you have time, and I would highly recommend you to do all these problems. Okay. All right. So so after this class, you should be able to finish the practice problem for chapter 5 to 6. Okay. So at the end of last time, we stopped at the ozone-analysis because it's quite a complicated reactions, and its mechanism is well beyond your current knowledge, right? So I'm going to go over it once more. Okay. So the next result of the ozone-analysis is that, as I mentioned, you cut these carbon-carbon double bond. All right. And for each carbon-carbon double bond of your of the carbon you cut, so you link it with a double bond O. Okay. In this case, you have 2 aldehydes. And in this case, you have 2 ketones, right? Each carbon connect to a double bond O, right? And in this case, you have 1 ketone, which is connected to here, and 1 aldehyde. All right. And close some of this. It's become very slow. So the mechanism involves 2 cyclic, what we call the ozonide. So ozonide, basically, it's 5 membrane structures with 3 oxygen in it. Okay, we have 2 types of ozonide. One is a mole ozonide, the other one is ozonide. All right. So a detailed mechanism, as I point out here. So the ozone itself can be viewed as a molecule with both a negative charge and a positive charge. All right, and it will undergo a concerted mechanism with the alkene. And the negative charge will attack this carbon. And once this carbon is attacked, the electron must be broken, the bond must be broken. Okay, so the broken electrons will go to this oxygen. So kind of do cyclization reactions. Now you will form a mole ozonide, which has 3 oxygen on the same side. Okay, 3 oxygen are linked. All right, then the next step is the breaking of the carbon-carbon bond. So in this step, so 1 lone pair of the oxygen will go back to form a CO double bond. Okay, once the CO double bond is formed, this carbon-carbon bond must be broken to keep the valency, right? And once it broke, another carbon-oxygen double bond is formed. All right, and this will also at the same time, it's a concerted mechanism, breaks the weak oxygen-oxygen bond. Okay, so after this concerted process, you will have two carbon-oxygen double bond. One is here, the other one is here. So 3 oxygen are still here. All right, then another cyclization, 3 arrows again. All right, because this is polarized towards the oxygen, this is partially positive, and you have an oxygen anion. And then you can imagine the oxygen anion will attack this carbonyl, and the CO double bond broke to give this CH2, and this CO bond also broke to give the electron to the positive. Okay, it starts with a negative charge, and the electrons eventually goes back to the oxygen charge, the positively charged oxygen. Okay, then we generated the ozonide. Okay, 3 oxygen are still here. So the final step is what we call the reductive walk-up. So this step is usually written here. So the first step, you generate the ozonide, and the second step, reductive walk-up using zinc. So zinc in this reaction serve as a reductant. Okay, so if you understand that zinc is a reductant, it's easier to understand the mechanism. All right, so the zinc has oxygen has a pair of electrons to offer. Okay, it will attack the oxygen, then 3 arrows again. So CO bond forms, this CO bond broke. I form another CO bond, double bond here, and give the electron back to oxygen. Okay, so the net process is that of all the 3 oxygen of ozones, 2 become bonded to carbon. Okay, this CO double bond, this CO double bond, and 1 oxygen goes to zinc, and zinc is oxidized to zinc oxide, which has zinc oxygen double bond, and the organic molecule, the alkene, is also oxidized. All right, 3 oxygen, 2 goes to the organic part, 1 goes to zinc. So this is the detailed mechanism of ozonolysis. So after we finish the ozonolysis, which is this part from alkene, we can generate a carbonyl compound by cut this carbon-carbon double bond. So we actually, in the past 2 weeks, we have covered all these reactions of alkenes. Okay, and I know it's complicated, but this is how difficult the organic chemistry are. Okay, so you need to understand. In order for the alkene to be transformed to all these functional groups, what regions do you need? And what's the condition? And you have several selectivities you need to care about. Regional selectivities, so what constitutional isomers will be generated or not. And there is sterol selectivities, and there is sterol specificity, which means that if you put a different stereoisomers as the reactant for these reactions, would you generate different stereoisomers of the product? Okay, and of course, the base, the foundation of all these selectivities is the mechanism. So I would say if you understand all these mechanisms of these transformations, you will understand whether the selectivity is, what the selectivity is. Okay, and for each reaction, you need to understand: is this an oxidation, or is this a reduction, or is this barely adjustment, not redox, not oxidation or reduction? So, for example, if alkene react with the let's see, water to give alcohol here. So, as I made a joke, so it's like it's called hydration. It's like drinking water. So 1 CH bond forms, 1 CO bond forms. H is less electronegative. O is more electronegative. Okay, so in the overall transformation, it's neither an oxidation nor a reduction. So it's like drinking water, then oxidize or reduce it. All right. So after completing this chapter, you should be able to understand the basic mechanism of electrophilic addition and all these mechanisms and the outcomes of the reactions, focusing on alkenes. And again, you also need to apply reactions to the synthesis of target molecules. Okay. So before we go on to chapter 7, so I would like to have some class practice. Okay, in this time, I know we don't have a lot of interactions between us because it's a Zoom session. And if it's a face-to-face teaching, I would ask you to do these problems and give you several minutes. And because I have calculated time, so basically we still have some time left. So it will be beneficial for us to do some practice and for you to practice. Okay, that's the most important. Okay, so and I have selected some questions and problems from actually midterm of past years. All right, so these are the real problems of the midterms that has been tested. All right, so for example, one type of questions I would ask you in the midterm is that ask you to suggest the starting materials for the reactions. Okay, so let's say if we have this product, so what's the starting material? If I give you the region and the reaction conditions. Okay, so I would give you, so for this problem, I would suggest that you have 3 minutes at most to do that, all right? So I will give you 3 minutes to figure out what's the starting material for this reaction, all right? And then after you finish, I can explain this question. All right, so 3 minutes, counting now. All right, so did you get the starting material? All right, so I will explain this answer. All right, So I think we did a similar problem last time. So the key for this type of problem is that you need to figure out what's the reaction first, right? So you have the chloride, and you have the 2 chloride here. So it looks like it's an electrophilic addition of dihydrogen. Okay, so and no, okay, so the reaction is electrophilic addition of X2. All right, and then you need to know the mechanism of this reaction, and you will figure out it's an anti-addition, right? It's an anti-addition. Okay, so as I said last time, for you to know that it's an anti-addition and to suggest the starting material, you need to make the product look like anti, right? And I think many of you still don't quite well, visualize this molecule. So how do I put it in the anti? So I will show you here. So to put it like an anti-addition product, you first need to put the chloride in the opposite, right? So the trick is that this bond can be rotated. All right. So many of you don't understand that or use that very often. Okay. So a single bond, a second bond can be rotated. So if you rotate the chloride and you take this single bond and put the chloride in the opposite position, so on the right part, what you will have, so this bond is here, and if we put the chloride in the perpendicular position, okay, basically you put the chloride in rotate like 30 degrees. All right. And then if you rotate this bond, what you have is a bold bond pointing up, pointing to you. It's a butyl group, all right? And the bromide will be behind it. Okay, this is the right part, all right? Then for the left part, for this bond, so you need to understand that there is a hydrogen we didn't draw here. Now you need to put the chloride, this chloride, into the same plane as this chloride, but pointing down, okay? So what we draw is here, okay? Chloride pointing down. And then once you put the chloride in the pointing down in the same plane as this chloride, then you will have to rotate back, right? And then the hydrogen will be pointing back. And the big phenyl ring will be pointing in the front here. All right, so basically this is how you understand the anti-addition. You put this chloride and this chloride on the same plane, and then after you have put it on the same plane, you have a different orientation of these 4 groups. The phenyl is pointing to you, and this butyl is pointing to you, and this hydrogen pointing in the back, bromide pointing in the back. Okay, so this can be visualized as the anti-addition product. So, and the anti-addition usually goes through if it's bromide, it goes to a brominium ion, right? For the chloride, chlorine ion. So what does that look like? Okay, so if you further, let's see, you draw a 3-membrane chloride plus. Okay, and then let's say this chloride is this chloride. Okay, then you will still have butyl pointing up to you, and the bromide pointing back, and the phenyl pointing up to you, and the H pointing back. All right, so everybody can understand this, right? So basically, this chloride will attack here to open this bond to give this chloride. Okay, so I'll draw it here to understand. Okay, this is how this anti-product is generated. Okay, so then if you draw at this stage here, it's easily understand, right? So the H and the Br for the original alkene will be on the same side. So what it looks like would be the H and Br will be on the same side, and the phenyl and the butyl group will be on the same side. Okay, then after you proposally figure out the starting material, then you can go like in the forward direction, see if it's right. So if this is the starting material, it reacts with the chlorine, okay, and the chlorine is it will attack here, here. Then you generate a three-member ring, okay, and the three-member ring will look like this alkene with the phenyl and the butyl on the same side, phenyl, butyl, and the HBr on the same side, okay. Then a chloride attack here to give this one, right? And this one, if you rotate this bond, will looks exactly like this one. Okay, so that's how you figure out how to draw the starting material for a reaction. Okay, so the second problem is here. Right. So in this problem, you have a dichloride. So one chloride is in the terminal position, and the chloride here is in the internal position. And you can see from the waved bond, so this chloride is not stereoselective formed, stereoselectively formed. Okay, it can be pointing to you, or it can be pointing to the back. Okay, so keep this in mind, and also keep this chloride within the terminal position in mind, and try to give the starting material. All right, I'll give you 3 more minutes. Oh, let's see. Did I draw extra? Oh yes, I drew the extra carbon on here. Okay, but you know what I'm talking about, right? Okay, so extra. Okay. So all right. So yeah. Okay. Now figure out this problem. 3 minutes. Okay, so in real exam, you really need to solve this type of problem within 3 minutes. Okay, there are more difficult problems in the midterm, so these are actually the easy ones. Okay, so 3 minutes. All right, so did you figure it out? So the key, oh, let me see. Oh, you don't need to show the steps, all right? for questions like this, if I just say suggest the starting material for the following reaction, just give me starting material, okay? And you don't need to give me the process of you getting that. I'm showing you the process just to help you solve the problems, all right? So if I want you to show the mechanism or the process, I will clearly state the problems. All right, so let's get this one. So what we have here, we have HCl, right? Okay, then we have a chloride in the product. So what you can figure out, maybe, okay, so it is the electrophilic addition of HX, all right, so it starts from alkene. Then if we slightly review the electrophilic addition of HX, okay, we have an alkene. So this means our group means it can be any group, okay. And then we have HX, let's see, HCl, okay. So we attack here, take off the chloride, right? And it follows the very important Markov-Nikov rule. So means the H will goes to the carbon with more H, which is here. Then you will generate a carbocation, right? And then with 3H here. And the carbocation, because it's a planar structure, so it's a non-stereo selective, which means the chloride can attack in the bottom phase or in the upper phase. So that means the product. So here are 3H. The carbon chloride bond is non-stereoselective, okay? So if you keep these in mind, it's quite easy to figure out this part, right? So you have 3H, 1 chloride. All right, so that is from the addition of the HCl. So let's see, is the addition of HCl with so with this diene, so because we have this HCl here. But how about this one? It's anti-Markov-Nikov, right? Because the chloride now goes, if it starts with alkene, the chloride now goes to the carbon with more H, not the H goes to the carbon with more H. So this one is wrong. So we cannot, if we start from this diene, we cannot, with excess HCl, we cannot get this one. So that's the tricky part of this problem. Actually, Professor Chu got this problem in her exam. So the correct answer of this is that, so since you cannot get this chloride from the alkene, so the starting material should already have this chloride. So the correct answer for this problem is this one. So if you react this monoalkene with the HCl, then the H add to this, Cl add to here, becomes a non-stereoselective Cl here, carbon chloride bond. Okay, then you get what this product. So if you write this diene, it's wrong because it doesn't follow the Markov-Nikov. Okay, Markov-Nikov rule here. All right, so this is a little bit tricky. But if you do understand the mechanism of Markov-Nikov addition and the addition of HX, then you should be able to figure this out. All right. So another type of question is that I would give you the starting material, and I will give you the condition and the regions used, and you need to write the product. And if I want you to write the product, I will say, oh, just write the product. But if I want you to write the mechanism towards the product, then you need to write the mechanism, okay? For example, in the description of the exam here, okay, so you need to first write the detailed mechanism, all right? And the mechanism towards the structures of the major organic products, okay? So you can't write the anti-Markov-Nikov. If it's a Markov-Nikov product, it's the major one, all right? You don't need to write the anti-Markov, and you shouldn't, okay? And also, another thing you need to understand is that show only diastereomers. So if two products are enantiomers, you don't need to draw both of them, okay? And if two products are diastereomers, then you need to write both products. Okay, and this one to make it clear that we know which product you are giving. Okay, so for the final products, so I will give you 3 minutes again. Oh, this one you probably because you need to write the mechanism and it requires more time. So I will give you like 5 minutes to write the product and the detailed mechanism of this reaction. All right, and counting now. All right, did you get the answer? Okay, so again, first look at the reaction conditions. So excessive HCl, and look at the starting material. You have an alkene. Pretty straightforward. Okay, so electrophilic addition of HX, right? And then what's the selectivity here? So Markov-Nikov, right? So, and then the H adds to more H, okay? So many of you may not understand what's, may not see clearly what's the, this look like. So this is equal to, if you draw a 6 number in here, looks like here. And the isopropyl group is pointing down, right, in this carbon. Okay, so the first step of HCl addition is what? Is the attack here. And because it follows Markov-Nikov's rule, so the H goes to more H, which is the carbon is to 2H here. Okay, then you can draw the product of the first addition step. And because you have H added to here, right? H, H, H. And what's the product? A carbocation here. And then you have the isopropyl group here. And then you have a chloride anion. Okay, to have full marks, you really need to follow the ways how we draw mechanism, how we teach you the mechanism here, all right? And okay, the second step is the recombination, right? So the chloride will react with the carbocation here, right? So, but you need to understand one thing is that we talked about the addition of HCl in class. So what one issue we need to care about? So about carbocation. So what can carbocation do? So carbocation can rearrange, okay? And if it can generate a more stable carbocation, it will rearrange, okay? So first, before we draw the next step, let's see whether this carbocation we draw here will rearrange or not, okay? Will it generate a more stable carbocation, okay? So let's draw on this structure, all right? So we generate a carbocation, CH3, carbocation here, okay? If we have the H here, so if rearranged, so what will we be? So the H will bring the 2 protons with it, not 2 protons, 2 electrons, sorry. So it will become the H3, H migrated here, carbocation become here. So this is a tertiary carbocation. This is secondary carbocation. So the secondary carbocation is less stable than tertiary carbocation. So the rearrangement won't happen. All right. So, and you don't need to show me this process on exam, okay? But you need to understand if there is possibility for the carbocation to rearrange, it will rearrange, and you need to draw that rearrangement product as well as the normal Markov-Nikov product, okay? As I mentioned in my slide, if you forgot, go back to the slides when I teach the carbocation rearrangement. I specifically mentioned that if there is possibility of rearrangement, you need to write down both the Markov-Nikov addition product and the rearrangement product, okay? Keep that in mind. But in this case, in this specific problem, it won't rearrange because it generates less stable carbocation. So you don't need to write, and you shouldn't write the rearrangement product, okay? Then another thing about this HS addition is that the stereochemistry, all right? So because this carbocation here, it is a planar structure. You can understand that, right? So the chloride has 2 ways to add it. So one way is the chloride will add here, okay? So in the top phase, we say A, pathway A, path A, okay? Another way is that chloride can add into the bottom phase, okay? We can say this is path B, right? So each way. So let's see what the product will be. Will it afford when we add in either way? Okay, if add in the top face. So pass A. So you have a 6-member ring again. So are you good at drawing the chair? So if you are not so far, so remember there is a practicing sheet of the chair drawing on the Moodle. Okay, so pathway A. So the chloride is on the top face. Or okay, so in this one, so this carbon chloride on the top face, and the methyl in the equatorial position. And if you draw it in the ring, okay, so the chloride will be on the top, methyl below, and the isopropyl also below. Okay, and then what about pass B? So you have a chair. So I draw this ugly again. It's because Apple Pencil, not because of me. Okay, so you have a chloride now in the bottom. In the top, you have CH3, and you have isopropyl, which if you draw a 6-member ring, it will look like now the methyl on the top, chloride on the bottom, isopropyl on the bottom. Okay, so in both cases, you will generate one product, and the one product, okay, if you look at the two products here, so what's the relationship between them? Are they enantiomer or diastereomer? So they are diastereomer, right? So because, for example, this carbon and this carbon, they are the same configuration or same assignment, but in this carbon it differs. So it's not a mirror image between them, okay? So that they are diastereomers. And as I mentioned in the problem, you should show only diastereomers. So for this, for you to get a full marks of this, you need to draw the mechanism of the electrophilic addition of HX, which is shown here. And you need to understand this carbocation is a planar structure. And you need to understand that in this particular case, the carbocation will not rearrange to a less stable carbocation here. So the only way for it to move forward is for the chloride to either attack from the top or from the bottom. And if it's from the top, it will generate this, bottom, another one, and these two are diastereomers. And to get full marks, you need to write these diastereomers. Okay, so all right. So this is this type of problem where you should write the mechanism and the product. All right, so I think we will go to the next chapter, and we will have more practice at the end of the next chapter. How do I close this? All right. Okay, let's go to chapter 7. Okay, so we just talked with you about the alkenes, right? So in chapter 7, what we will talk about is another type of functional group, which is the alkynes. Yes, so first, here are the learning outcomes of this chapter. So you need to understand the structure of alkyne. Most importantly, so the midterm one will cover chapter 1 to chapter 7. So that means the chapter of alkynes here today, what I teach today and the next or this Friday will be covered in midterm. All right, so chapter 1 to 7. All right, and anything beyond the 1 to 7 won't be covered in midterm 1. Okay, so you need to understand the structure of the alkynes and how it is related to its physical and chemical properties. And you need to mostly chemical properties, and you need to understand the mechanism of the reaction of alkynes, which is as an extension of the reactions of alkenes, but there are some differences, and you need to understand that. And also an important part of chapter 7 is that we will start to think about retrosynthetic way to synthesize a molecule and how to design a successful synthetic route towards the target molecule. So I would say it will not be a major part of the midterm 1, but in midterm 2 and the final exam, so there will be a lot of marks focusing on if I give you a target molecule, can you use all the reactions you have learned in this class to devise a synthetic routes and successful synthetic route towards that target molecule, okay? And we will touch a little bit on the concept of brain chemistry, but it's not really the focus of this class. Okay. First, we need to understand the structure of alkynes. So alkyne is linear. Okay, so it's like R, C, C, R. These four are in a linear structure. Okay, and so carbon-carbon triple bond results from the sp orbital, which are these two carbons, and forming a sigma bond. Okay, this is the sigma bond, and unhybridized px py orbital to form 2 pi bonds. So so this is the alkenes. So if you compare alkenes with alkynes, you will see the alkenes has 1 pi bond, right? This p orbital form a pi bond with another carbon's p orbital, and because it's side by side, so it has 2 faces. So one is the top face, the other one is the bottom face because of this planar structure. So alkyne proceeds more. So it not only forms pi bond, it forms 2 pi bonds. So one, and they are perpendicular. They are like 90 degrees apart with each other. So they are linear. So one pair is bottom, top, and one pair is left, right. Okay, so they are 90 degrees apart. Okay, and so breaking a pi bond is very hard. So as I told you that breaking this pi bond in the alkenes is already very hard. It requires 268 kilojoule per mole. So because now we have 2 pi bonds, okay, so more bonding, more sharing of electrons. So actually breaking the pi bond in acetylene requires 318 kilojoule per mole energy. So we should say overall the triple bond is shorter and stronger than single or double bonds. Okay, it's really hard to break these pi bonds, okay, and rotate it. Okay, and also like I said with the alkenes, the rotation is blocked. Okay, and the remaining sp orbital, as I said, will form bonds to at 180 degrees. Okay, like here. So because this red one are electron density, if you understand that. So and because there are two pi bonds, the electron density is very high, so it's red. All right, and it's 180 degrees because it's a sp orbital. All right, so the naming of the alkynes is as a brief review. All right, so you need to number the chain with triple bond to give the smallest number to the triple bond. Okay, so for example, this is a 1, 2, 3, 4. Okay, 1, 4 diene. So you cannot say 1, 2, 3, 4, 4, 5, 6, 7, 4, 7. You cannot say 4, 7. You need to give the smallest number to the triple bond. Okay, and then compound with 2 triple bonds like this one is called diene, and triene as extension has 3 triple bonds. Okay. And an enine has a double bond and a triple bond, so it's a multifunctional molecule. Okay, so and when you see this kind of problem asking you to name an enine, you need to include both the ene, the alkene, and ine, the alkyne, into the parent chain. Okay, so the parent chain must contain both double and triple bonds. Okay, so in this case, so although you see this carbon chain is much longer, right? It has 4 carbon here, but because it's an enine, so you need to name put this one as the parent chain because this one has both the alkene and the alkyne in it. Okay, and for example, if you name this one, you have a 5-heptene ine. That's the way you name enine. Okay, and you cannot say put the numbering as 2, 6. Okay, one side is 2, 6, one side is 1, 5. You need to pick the 1, 5 because 1 is less than 2. Okay, so for example, this one should be 1, 5, should not be 2, 6 due to the same reason. Okay, so we will have a brief break. We will come back at 11:30. Okay, and then I will show you further. It's okay. So, but if an atom is connected to a CH2, then connect to an alkyne, we call it a propagyl group. All right, so this you need to memorize. And like in alkene, if it's connected to a double bond, it's called alkenyl group. If it's connected to a CH2 alkene, it's called allyl group. Okay, in this case, it's called a propagyl group. Okay, and then we have, for example, in comparison, for an alkyl group, C4, we call it a butyl group. Okay, and then if it's an alkene, we call it a butyl 1-enol. So, which is also a vanillic group because it's connected to the carbon. Okay, and then for if it's an alkyne with 4 carbon and this double triple bond is here, we call it a but 1,9 enol group. Yeah, that's pronunciation is stupid. Anyway, so but just write down as this. Okay, and like the alkene, there are two types of carbon. Okay, one is in alkene case, one is vanillic carbon, which is the alkene. Okay, another one is allylic carbon, which is the CH2 connected to the alkene. So in this alkyne case, there are also two types. One is this sp carbon in nature is called the alkynyl carbon, and this carbon, like the propagyl group here, it's connected to the sp carbon, but it's next to it, so it's called a propagylic carbon. Okay, keep these concepts in mind. And there are also other terminologies I need you to memorize or keep in mind. Is that so we have a symmetrical alkyne and unsymmetrical alkyne. So symmetrical alkyne means the two substituents of the alkyne are the same. So for example, in the ethine case, the two substituents are 2H, which are the same. So in the 3-hexyne group, so this is an acyl substituent. This is also an acyl substituent. So this is a symmetrical alkyne. All right. And but for this one group, one side is 1, 2, 3, 4 carbon, and the other one is H. So it's an unsymmetrical alkyne. Also, if one of the substituents is an H, like these first two cases, we call it a terminal alkyne because apparently the triple bond is at the terminal. Okay. And if the two substituents are not hydrogens, then we call it an internal alkyne. Apparently, it's because the triple bond is within, it's inside of the chain. Okay, it's not no H at all. It's internal alkyne. So the shapes would look like this. See, terminal alkyne with an H, internal alkyne without an H. And a trend of the stability of alkynes is that if the alkyne has more substituents, it's more stable. Okay. So for example, this one is much stable than the ethine, and it's the similar trend as the alkene. And do you remember why? It's because hyperconjugation, right? So because more substituents will donate or spread its electrons of this sigma bond into the anti-orbital of the alkyne, all right? And just like the alkenes and just like the carbocation. So more substituted the carbocation, more substituted alkene, more substituted alkynes, they are more stable than less substituted counterparts. Okay. Okay, so internal alkynes more stable than terminal alkynes. So 3-hexyne more stable than 1-hexyne, and also more stable than ethine. All right. So further comparison between alkenes and alkynes. Okay, both are unsaturated. Still understand the unsaturation, right? Because it's not bonded to enough hydrogens. Okay, enough groups. So it's unsaturated. As thus, they will undergo similar reactions, but differences exist. So what does that mean? So for example, if we do the addition reactions to alkynes, just like the addition reactions to alkenes, okay? So these XY will add into 2 carbons of this double bond. Oh, the first addition will generate alkene. Okay, X to this carbon, Y to this carbon. Okay, then we can have a second addition, and the second addition is just like the addition of alkenes, right? So we can A goes to here, B goes to here. Okay, so just like alkenes, electron-rich pi bonds of alkynes will undergo electrophilic addition, but alkynes has 2 pi bonds. That means we can have first addition and the second addition, but more complicated than alkenes because the addition can happen twice and each addition should have issues of regioselectivity and stereoselectivity. Okay, so unlike alkenes, you can add just the once, but for alkynes, you need to consider both steps. Okay, what's the stereochemistry regioselectivity of the first step, and what's for the second step of the alkyne addition. That's the something more complicated than alkenes, and we will talk about it in detail. So alkynes can react by addition to similar electrophiles with alkenes, for example. It can add to HX, add to dihalogen, and add to hydrogen gas, hydrogenation, right? And add to water, which is the hydration. So instead of alkene drinking water now, so this is the alkyne drinking water here, okay? It can also undergo the oxymercuration, demercuration reaction like alkene, also hydroboration oxidation reactions, okay? But besides all these addition reactions, terminal alkynes and different from like terminal alkenes or alkenes with 2H. So terminal alkyne has its special reactions, which I will talk about it. Okay, so first, let's see the difference in the similarity of addition of HX between alkynes and alkenes. Okay, so first, addition reactions of alkynes, the similarity between alkynes and alkenes is that they both follow Markov-Nikov addition rule. Okay, so let's say this terminal alkyne. So this carbon 1H, right? This carbon 0H. So this carbon is the carbon with mole H. So if you follow the Markov-Nikov rule, the H will add to the carbon with mole H. Okay, so the blue H will goes to here, and bromide goes to this internal carbon. So this follows Markov-Nikov selectivity. And as I mentioned, it can happen twice, right? Because it has 2 pi bonds. So the signal one is just like the addition of the alkene. All right, and the blue one will go to carbon with no H, which has this carbon having 2 H's, and this carbon no H. Okay, so the second blue one will add into here to generate this carbon with 2H, and the bromide will become a dibromide in this case. And for this kind of molecule, the IUPAC name is 2,2-dibromohexane. We usually call if the carbon has 2 bromide bonds, 2 bromide substituents or 2 similar substituents, we call it a germinal dibromide or gem dibromide. So if this chloride is a germinal dichloride and gem dichloride, okay? Even with methyl, okay, if these bromide are methyls, we can call it germinal dimethyl, okay, or gem dimethyl, okay? So the mechanism of the addition to alkyne. So if we review this addition to alkene first, so the electrons here, the pi bond electrons, electron-rich pi bond, will adding to the H, kick off the bromide to generate the alkyl carbocation. Okay, the alkyl carbocation can recombine with the bromide anion to form this alkyl bromide. So how about the alkynes? So after the first addition of alkynes, you see the positive charge is not on the alkyl group anymore, right? Compared with this. So the positive charge, the carbocation, is now a vanillic carbocation. Okay, the positive charge is on the sp2 carbon, and then the bromide recombine with the positive charge to generate the vanillic bromide. Okay, so if we want to understand the characteristic properties of the addition of alkynes, so apparently the properties of these vanillic carbocation is important. So how about vanillic carbocations? So as we have learned before, so carbocations, relative stabilities of carbocation follows this trend. So 3 alkyl group tertiary is more stable than secondary, secondary more stable than primary, primary is more stable than methyl carbocation without any alkyl group substituents, right? Because of hyperconjugation. Okay, so we can fill the gap with the secondary vanillic carbocation and primary vanillic cation. Okay, so the trend is that secondary alkyl carbocation is more stable than secondary vanillic carbocation, more stable than primary alkyl carbocation than primary vanillic carbocation. Okay, so there is a reason for this trend. Okay, so secondary vanillic carbocation are about as stable as primary alkyl carbocations. Okay, so secondary of the vanillic one is similarly as stable as the primary. Why? Right? So because secondary vanillic carbocation is the carbocation is on a vanillic position, which is like here. Okay, and because it's sp2 carbon, and the it's sp hybridized carbon, and the sp hybridized carbon has more s character, and that means this carbon is more electronegative carbon. And imagine, so if a carbon is more electronegative, it wants more electrons, right? Because it wants electron to come to it. Okay, but if you put a positive charge on it, that's ridiculous, right? So it wants more electrons, but you derive it of the electrons, so you don't give it any. So it's pretty unstable. Okay, so secondary carbocation, secondary vanillic carbocation compared with its counterpart of the alkyl carbocation is less stable. Okay, understand that? Okay, so the trend is like this. So secondary vanillic carbocation is similar as primary alkyl carbocation, but is much less stable than secondary alkyl carbocation. Okay, so it's a little bit complicated. Okay, but just keep this trend in mind. All right. So as we said, protonation of the alkynes generate vanillic carbocations, right? So and another possible intermediate people has been arguing for or arguing about is that some people don't, or some research point out that it may not be a carbocation at all. So it has been argued that these are really not vanillic carbocation, but pi complexes. So what does pi complexes mean? Okay, it means like this looks like a brominium ion, right? Basically, the positive H here is complexing with the pi system to form a structure like this. So this we call a pi complex, all right? And this looks like brominium ion. And for the brominium ion addition, we know that it's anti-selectivity, right? Because another one, the chloride or the bromide will attack on the other side, the opposite side of the ion here, right? So, and the people arguing for the pi complexes has support. So their support is that most of the addition of HX to alkynes, they generate a Z alkene. Okay, it's an anti-addition. So the H and the chloride are on the opposite side of the alkene. So they think that this is the reason why they put forward intermediate, not like a vanillic carbocation, but more as a pi complex. Because the pi complex, the same side is blocked, and the HCl has to come to the different side. And if the Cl comes to the different side, it will generate the Z alkene. Okay, so to summarize that, so the addition of HX to alkyne, in most cases, will generate an anti-addition. And the anti-addition is one of the supporting reasons why people think this intermediate may not be a vanillic carbocation, but a pi complexes. Okay, this is a little bit complex to put on the exam, so I won't test you. Okay, I have an alkyne, I have HX, give me the single addition, and you have to write the Z. Okay, normally if I put it on the exam, I will be more specific. For example, I will say, okay, I give you an alkyne, so instead of at once, I will ask you, so if I have excess amount of HBr, what's the product? So you would avoid writing the EZ of this. You will directly write, oh, okay, the final product of addition twice is this dibromide product. Okay, now you don't need to write this one if I give you excess amount of HBr. All right. So another comparison between alkyne and alkenes is relatively stability. Okay, so alkynes itself is less stable than an alkene. Okay, all right, and so alkynes are more reactive. Okay, but another thing about the alkenes and alkyne is that the addition of HX to alkene and alkyne, their relative stability of the transition state is larger. So that means the transition state of the alkyne electrophilic addition is much higher than the alkene. Okay, so imagine, let's do a simple calculation. Okay, so if the transition state of these two are the same, Okay, and because of the alkyne are less stable, that means it's easier for alkyne to reach the transition state if the transition state are same, right? So the alkyne are more reactive in the addition reaction. But this is not the case. The case is that the difference between the transition state energy is larger than the difference between the alkyne or alkene starting material. So in order for the alkyne to do the addition, the activation energy, which is shown in green, is much bigger than the activation energy of the alkene during the addition reactions. So in the electrophilic addition reactions, so the alkyne is less reactive than an alkene because the activation energy, not because of the starting material. Okay. So as I said, alkynes can add 1 or 2 molecules of HX, and each follows the Markov-Nikov's rule. So this is another example. For example, if I give you 1, 2, 3, 4, 5, 6, 1 hexyne, and react with HCl. Okay, so the first addition and Markov-Nikov addition, so the H will go to here with 1 H, right? You will generate either a vanillic carbocation, or people argue, okay, it's a pi complex, it's different than the vanillic carbocation. But you will definitely not generate it is this anti-Markov-Nikov carbocation. Okay, so the chloride will always add it into the internal position because it follows Markov-Nikov's rule. And then after the chloride add into it, it will generate the alkene. Okay, then let's consider the second electrophilic addition, and the second one should also follow the Markov-Nikov's rule. Okay, now let's see which carbon has more H. So this terminal one has 2H, and internal one 0H, right? So the second one, if it follows Markov-Nikov's rule, the blue H will also go to the blue H side, right? To get this one, the carbocation generated in the internal position. This will not be generated at all because it's anti-Markov-Nikov. Okay, so after carbocation generated, chloride adding to here to give this carbon with 2 chloride. Okay, what is this called? This is GEN di. It's called a GEN dichloride, right? And so for the regional selectivity, both addition steps follow the Markov-Nikov's rule. And for the stereochemistry, for the first step, it may go through the pi complexes, so it's usually anti. And for the second step, because it generates alkyl carbocation and has both faces open, the chloride can attack from the top face, or the chloride can attack from the bottom face. So for the second step, there is non-selective stereochemically. Okay. And then the X2 addition. So X2 addition, okay, the alkyne follows the X2 addition, undergo anti-addition to alkynes. Okay, so if you still remember the alkene X2 addition, it goes to brominium ion, right? So that makes them an anti-addition. So this is the same with the alkyne. Okay, so if the alkyne only adds the let's say 1 molecule of Br2, okay, it will generate a pi complex, which looks like a brominium ion. Instead, the brominium ion has a CC double bond in it. Okay, it looks like here, and then another bromide attacked from the opposite side. So now the 2 bromide is at the opposite side of the alkene. So it's anti-addition, give you a trans or not trans. This is Z. This is E double bond. Okay, and so if it add twice, it's actually much simpler, right? Because you don't need to consider the double bond geometry because it will be added to a second chloride to give this fully substituted alkyl. Okay, so the first one is anti-addition, 2 chloride on the opposite side of the alkenes, right? And the second one will add into this 2 carbon. So each carbon now has 2 chloride. Okay, GEN dichloride, GEN dichloride. Okay, to summarize it, the first addition is anti, gives a trans dihaloalkene as intermediate, but 2 equivalents of X2 give tetrahaloalkene as product. Okay, just like here. Okay, then how about the reduction of alkynes? So if we use a hydrogen gas to reduce the alkyne, it will follow a similar pathway as the hydrogenation of alkenes, right? So it's cis addition. So usually for the alkynes, we usually use the similar catalyst as the alkene hydrogenation. So in this case, we can use the palladium/C, which means it's a palladium on carbon or platinum on carbon. Both can be used to reduce alkyne. But one thing about the addition of H2 to alkyne is that it cannot stop at the alkene because they are the same catalyst for the alkene reduction. Okay, once it generates alkene, it can also be reduced as the alkene to the alkyne, alkyl, right? So because this is the same catalyst, the same catalyst can catalyze the hydrogenation of the alkene. So the intermediate of the alkene cannot be stopped here. It will be further reduced, all right? So cannot stop at alkene directly to alkene. Keep that in mind. But it is possible, as organic chemists found out, to stop at the alkene. All right. So, but this partial reduction usually requires a different catalyst. So, for example, here, so there is method to reduce the alkyne directly to cis alkene, which is in addition, which we use is a Lindlar catalyst. So Lindlar catalyst is chemically deactivated palladium on calcium carbonate. Okay, so this is kind of inorganic chemistry, but you don't need to understand that. But remember, Lindlar catalyst can stop at cis alkene. All right, so you have palladium on carbon, it cannot stop at the alkene. It will directly go to decay from phi design. But for the Lindlar catalyst, and it's different, it's at different selectivity, so it can add 1 molecule of H2 into here to generate cis by decay. Okay, so stop it here because the Lindlar catalyst cannot further reduce alkene to alkane, okay, to the saturated molecule. All right, so this kind of Lindlar catalyst is kind of is very, very useful in organic synthesis. So, for example, we have this retinol-related molecule with so many alkenes and 1 alkyne. Okay, so imagine if you use the palladium on carbon as the catalyst for the hydrogenation, all of these unsaturated bonds will be reduced. You will get a pure alkyne, right? But if we use a Lindlar catalyst, we can selectively reduce this alkyne to cis alkene here. And once it's cis alkene, this double bond will not be further reduced to alkane. Okay, and all the double bonds next to it, all of the double bond in the molecule will be preserved because simply because the Lindlar catalyst cannot further reduce the alkenes. Okay, so this is a very selective hydrogenation catalyst that stops at alkene. Okay, so as we said, so all these palladium on carbon and Lindlar catalysts, they give cis alkenes, right? So alkynes can also be reduced to trans alkenes. And in this case, what we use is dissolving metal reduction. So that goes to a different mechanism that gives exactly the opposite selectivity as the hydrogenation reaction. So in hydrogenation reactions of these 4 carbon alkynes, it will goes to the cis alkene, so the H will be on the same side. But if we use dissolving metal reduction, it will give the anti-addition product. And now you can see the 2 hydrogen on the opposite side, and this is the trans alkene. Okay, and this is the radical mechanism. Okay, I know we are talking about so many reactions and their mechanisms right now. So try to keep up with me. Okay, so so alkynes are reduced to trans alkenes with sodium or lithium liquid ammonia. So this is actually how the actual experiment looks like. So you can see this kind of solid here, right? Okay, so at minus 78 degrees, okay, the ammonia, which used to be a gas in the room temperature, now become a liquid. So this is pure ammonia. Terrible, huh? And then if you put a sodium chunk into it, it will become blue. Okay, blue is usually the color of radicals. Okay, so that means some radical is generated. And this beautiful color of blue. Then you put the alkynes into it, and what you got as product is the trans alkene. All right, and the alkali metals. So if you put the sodium chunk or solid into this ammonia liquid,
and it will act as a reducing agent, so the metal, and which means that they will give away electrons. And the sodium zero, if it gives away one electron, it will become a sodium plus, right? And the sodium plus is very common because you have salt, which is a sodium chloride, and with the sodium plus, sodium chloride and plus one oxidation state, right? But the sodium zero, the sodium solid, sodium metal is sodium zero, so it gives away electrons. All right. So how to draw the mechanism? So another concept, we taught you how to draw a mechanism with moving of a pair of electrons, right? We use this the full arrow. All right. This usually marks the movement of two electrons. For example, you have a pi bond. The two electrons of the pi bond here will move to an H. For example, HX to the H, and kick off the X2, the X, the halide, the bromide or chloride with two electrons. So this is the full arrow. So we can also draw half arrow. A half arrow is that the arrow with a single bar. Okay, you don't have this part. So the half arrow usually means the movement of one electron, and this is pretty common in radical chemistry because the radical is one electron. So okay, so if you move one electrons everywhere, you need to use the half arrow. So for example, this dissolving metal reduction going through one electron process. Okay, so the lithium or the sodium, as I said, it tends to give away one electron to become a lithium plus here, right? So one electron goes to here, and it's looking for another electron to pair it. Okay, so the pi bond broke. The pi bond has a lot of electrons. So one electron of the pi bond now goes to combine with the electron given by the lithium. Okay, now one electron from the carbon, one electron from the lithium. Okay, it forms a pair of electrons, which is here. And how about another electron that is shared, used to be shared with the electron given away? So it goes to this carbon. All right. So this carbon now accepting one electron. Now this becomes a radical, right? Because it only has one electron. And this is anion because this anion, one electron comes from this carbon, another electron from the lithium. Okay. So overall, this is the negatively charged, and the negatively charged can extract a proton from the ammonia. So this minus will attack the hydrogen, kick off the nitrogen, and the H, one H. So remember, this is the first H of the dissolving metal reduction. The first H will be given to the anion here. All right, and once the H is given here, you still have a radical, right? The radical is still here. Remember? Okay. Then the second step is that the radical will give out this electron, single electron, with another molecule of the dissolving metal. Okay, another lithium comes here, say, okay, I also have a single electrons, I want to share with somebody else. Okay, so, and the radical says, okay, I have one electron too, let's share it. Okay, so half arrow, these two electrons combined, now we have double electrons. Two electrons here, which is also anion, right? And the lithium becomes lithium plus. Okay, then the anion following this step, similar of this step, will try to extract a proton from the nitrogen again. Okay, once it extracts the proton, the second hydrogen is here. See, because in the first step, it generates a trans structure with a radical and an anion. So the first hydrogen will be trans to the radical, and the second hydrogen then will be trans to the first hydrogen. All right, did that understand? Huh? So, and another reason for this trans reaction is that usually the cis final anion is usually not favored in this case. Okay, so because there are some electron repulsion or something like that, but that is beyond this course. But you need to memorize the single electron mechanism for the dissolving metal reduction, and really keep in mind that this is different from the hydrogenation reactions, which gives the cis-alkene. The dissolving metal reduction gives trans-alkenes. Okay, so if I summarize all the reactions I talked about, about the addition reactions, and we can an interesting question is that how to control addition to alkynes to occur once or twice, right? So as I mentioned, so if you have the addition to dihalogen or addition to HX, dihalogen here or HX here, so you can simply control the equivalent of the region you add, okay? So if you add only one molecule of the chloride, one equivalent, the dichloride, so you can get the alkene. It only happened once, okay? The two chlorides are transferred to each other because it goes through an anti-addition and the chromium ion. Just remembering, right? But if you add excess amount, let's say more than 2 equivalent of chlorine, you get alkanes with a tetrahalo on it, okay? So you can just simply control the equivalent of chloride you added. So how about HBr? So if it's a terminal alkyne, it adds to one equivalent of HBr, the H will go to the H with more H. Now the carbon with more H, right? Markov-Nikov selectivity. So if you use one equivalent HBr, you get alkene, trans addition, usually. And then if you add an excessive amount, let's say more than 2 equivalent of HBr, then the second H will still goes to the carbon with more H, so you get a gem dibromide. Okay, so there is this interesting question about this control of reagent equivalent to control the addition once or twice. So for a terminal alkyne, like this 1-hexane, what is generated after I reacted with one equivalent of HBr, then I react with the then followed by one equivalent of Br2 addition. Let's say if I have these questions on the exam, I have 1-hexane. I say, okay, first reaction, one equivalent of HBr. Second reaction, one equivalent of Br2. Okay, what's the product? Okay, interesting question. Just think about it after class, all right? And for the addition of H2, you can control it by catalyst and the method about the cis or trans alkenes you get. And for example, if you use the Lindlar catalyst, you can stop at alkene. Remember that because it's Lindlar catalyst, but it's cis. But if you use the dissolving metal reduction, you can also stop at alkenes. Okay, but the selectivity is trans. So there is another arrow here. Think about it. If you have hydrogen and you have palladium and carbon, what's the product? It's alkanes. Okay, because it will be over-reduced. So it cannot stop at here. The palladium on carbon catalyst will not stop on alkenes. It will go directly to alkanes, which has all the hydrogens. Okay, fully saturated. Okay, I think this slide is pretty interesting, and you need to fully understand all these questions. And how about hydration of alkynes? So that is very different from, I would say, very, very different from the alkenes because there are special issues here. Okay, so mercury salt can catalyze the Markov-Nikov addition, and the anti-Markov-Nikov addition can be catalyzed by hydroboration, oxidation, and there are very deep mechanistic reasons between all these activities. Okay, so let's say if we have a terminal alkyne here, and if it's the first addition of water is HOH, right? The H added to more H here, so it will become this, right? And for the hydroboration, will become here because anti-Markov-Nikov, the H will go to the carbon with less H. Okay, so do it go further into a second hydration? No. Okay, this is the major difference between alkynes and the alkenes, because after the first hydration of alkyne, these enols cannot be isolated, and these enols will be isolated as ketone. Okay, again, need to pay attention to this. Okay, terminal alkyne, after the first mercury-mediated hydration, become Markov-Nikov alkene here. But this cannot be isolated. This will become a ketone. Okay, what happened? So the final product is a ketone, not the enol here, what we call the enol here. Because these two are tautomer, and these tautomer can interchange with each other really quick. That favors the side of the ketone. Okay, so the new concept here is called a keto-enol tautomerism. Okay, and the definition of tautomer is the constitutional isomers that rapidly interconverge. So what does that mean? So, and this is enol, this is ketone. They are constitutional isomer because all these, the constitution is the same, right? All these 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 5 carbons, okay? 1 oxygen. So, and they can interchange. So this can easily change into here. And the keto tautomer is more favored. That means once you have a little bit of this of enol in your reaction, it will convert it to the ketone rapidly. Okay, there's no way you can catch him because he will turn into the ketone rapidly. Okay, so this is this is another example. So this is an enol. It will convert to the aldehyde very rapidly. So this is enol. It will convert to ketone because there is a methyl substituent. But in this instead there is a H here, so it becomes aldehyde. It's become ketone. Okay. So this ketone enol tautomerism is one very important example of tautomerism. And for the hydration of alkynes, we observe the ketone as a product because the ketone form is usually much more stable compared with the enol. And because it is much more stable, the enol product will rapidly change into ketone. And what you get is the ketone as the product. And the mechanism for this tautomerization is usually depicted here. And this is the mechanism under acidic conditions. So what you do is that you have a long pair on the oxygen and go back to this carbon-oxygen bond. And to keep this valency, this pi bond will attack a proton on the hydronium ion and kick off water. Okay? Then you have a CO double bond here. And CO double bond now is positive charged because this hydrogen is not left here. Okay, then the water can act as a base to deprotonate this hydrogen to give back the ketone. All right, to form this ketone here. And if we look into the detailed mechanism of the hydration with a mercury salt, we can see the first several steps are similar as the oxymercuration, demercuration step. Okay. So the first, a concerted step, which the pi electron will react with electrophilic mercury 2 to form this kind of stabilized carbocation. And do you still remember what's this intermediate called? It's called mercurinium ion. Okay, and then the mercurinium ion can accept the attack from the water here. And it follows Markov-Nikov's rule because this positive charge is more stabilized by the substitutes here. Okay, then different thing happened. Okay, now this is the enol. This is the enol ion, the precursor for the enol. Okay, then the enol will be deprotonated by water to generate this mercuric enol. Okay, the mercuric enol can do the tautomerization. Okay, now this is a carbon-oxygen single bond. After tautomerism, it will become a carbon-oxygen double bond. Okay, are you keeping up with me? All right. So this double bond will be transformed to this double bond. Okay, it becomes a ketone. And in this particular case, this carbon mercury bond is very unstable. It can also undergo a reaction that releases the mercury. So this this electron will be taken here. This CO double bond will be broken to form enol. Okay, and the mercury is released, and the enol, as we mentioned in the previous slide, will rapidly tautomerize to ketone. So a lot of information to take in, huh? So due to this kind of mechanism, so we have first we have a Markov-Nikov selectivity just as the alkene, right? Second, we know from this mechanism that the demercuration occurs in the reaction. Okay, you don't need to add. So that's different from the alkene oxymercuration because for the alkene oxymercuration, you need to add sodium borohydride to remove the mercury, right? But for the alkyne, because this is so unstable, the mercury will be removed like a spontaneously in the reaction. So the mercury salt can be used in catalytic amount. Okay, do you understand the logic, right? So because during the reaction, the mercury salt is released. So the mercury salt can go back to the starting material. Okay, so you only need a catalytic amount of mercury salt to facilitate the reaction. Okay, unlike the alkenes. So unlike the alkenes, you need to add a sodium borohydride to remove the mercury. The mercury removes the interaction of the alkyne itself, so it can go back to the alkyne, react with another molecule. So the mercury is only used in catalytic amount. Okay, and another difference of the between the alkene and the alkyne oxymercuration is that the alkene oxymercuration usually use the mercury diacetate, and the alkyne usually use mercury sulfate because alkynes are less reactive. So remember the reaction diagram, right? And because it is less reactive, we need to use more electrophilic, more electron deficient mercury sulfate as catalyst. Okay, and as I mentioned, another difference is that this alkene, you need a separate demercuration step, but the alkyne, you don't need a separate demercuration step. And because of that, the mercury can be used in a catalytic amount. So how about the hydroboration of the alkynes? Okay, so it follows a similar reaction mechanism as the alkene hydroboration. Okay, so the first step is the H and the Br2 adding to the same side of the alkyne. Why it adds into the same side? Do you still remember that? Because it's a concerted mechanism consists of a four membrane, right? So the H will be here, the B will be here. So it will form a four membrane transition state. So it adding to the same side. Okay, then it is similar as the alkene hydroboration. So after the boration happened, you have the alkynyl bromine, and then when you use the oxidation step, it can generate a CO bond, replacing the CB bond. Okay, once the CO bond forms, look at this. This is a molecule of enol, right? Because the tautomerism will make it rapidly convert to the ketone as the product. Okay, and also the mechanism of the enol-keto tautomerism is different in this case because if you're using oxidation method, it's under basic condition because you're using a very strong base, sodium hydroxide. Okay, so the mechanism and the basic condition for the keto-enol tautomerism is listed here. So because we have a free hydroxide now, and it's very basic, it has a lot of electrons, so it will grab the hydrogen here and break the OH bond. Now the O minus is here, all right? The O minus will then happen to give the electron back into this bond to form the CO double bond as the final product, right? And this pi bond has to be broken because the valency has to be kept, okay? The pi bond will attack water and to give back the hydroxide, and the H will come into this alpha position of CO double bond here, so it will become a ketone. So it's quite a different mechanism from the keto-enol tautomerism and the acidic condition as I listed here. Okay, so in the mechanism and the acidic condition involve a hydronium ion, but the keto-enol tautomerism and the basic conditions using a hydroxide anion. Okay, so for example, for this mercury salt, because the alkyne is very special, we only have two types of alkynes. Instead of alkene, we have 4 substituents, right? So we have a symmetrical internal alkyne and unsymmetrical internal alkyne here. So for internal alkynes, only the hydration of symmetrical alkynes result in one product selectively. What does that mean? Let's say if you have symmetrical internal alkyne, so the water can add, the OH can add here, the OH can add here. And because it's symmetrical, so it doesn't matter which side it adds, right? It will always become the same product. So the O, either on this carbon or either on this carbon, will give the same product. The same product will always have a ketone with 2 carbon left, 2 carbon on one side, 3 carbon on the other side. Okay, so this is synthetically useful because only one product is generated. But for the unsymmetrical internal alkyne, the story is different because you will have now a mixture of product. Let's say if you the oxygen adding to here. If the oxygen adding to here, the ketone will be eventually generated here, right? So you will have this product. But the oxygen if added here, the ketone will be generated on the right carbon, which is the ketone with the two carbon on the left, with 1, 2, right? So this hydration reaction of asymmetrical internal alkyne is really not useful because it generates two products. But for the symmetrical, the two products are the same, so it's quite useful. Okay, so if we do a similar comparison between these addition of HX and X2, and how to control if they add once or twice, it's quite interesting. So for the addition of HX and X2, we can control by the amount of reagent, right? 1 equivalent to these two, 2 equivalent to these two. Addition of H2, we can control by using different catalysts or different method, right? So for the H2 Lindlar, we can get a cis hydrogenation product. For the dissolving metal reduction, we can have trans. And for the H2 addition using palladium on carbon, we can get an alkane, like the fully reduced product. But for the addition of water, you do not need to control between addition once or addition twice, because it does not add twice at all, because it stopped at the enol, and the enol will rapidly convert it to the ketone, so to ketone or aldehyde. So you cannot say, okay, I will add twice because the water will react with the enol again. No, because the enol is existing in very small amount of time. It will rapidly become something else that does not have the double bond. So it will stop. Okay, so from mechanistic perspective, it will not add twice. All right, that's very interesting comparison. Okay, next we are going to cover the terminal alkyne acidity and its special reactions with terminal alkynes. Okay, so so why the alkyne has such kind of reactivity that is different from alkene is because the alkyne CH bond, like here, is much more acidic than the alkenes and the alkane. Okay, so if you look at the pKa value here, still remember, the lower the pKa value, the higher the acidity. Okay, HF is the strongest acid, and the alkane, which has a pKa of more than 60, so it's a very weak acid. So the alkynes is kind of quite acidic. It's less acidic than water, but more acidic than ammonia, and it's much more acidic than the alkenes and the alkanes. Okay, and the reason behind the enhanced acidity of alkyne CH bond and because the hybridization. Okay, so we have alkane, sp3 carbon, alkene, sp2 carbon, and alkyne, sp carbon. Okay, if you count the component S component in each of these hybridization, LQ is 25% ACE, vanillic is 33%, and acetylide has a 50% of ACE. So as I mentioned previously in chapter 1, 2, 3, more S character means more electronegative, right? Because the S character is closer to the nuclei, okay? It's very close to the center of the atom. So it draws electrons to the center of the atom, so it's drawing electrons more. So if you have more S character in your orbitals, it means the carbon is more electronegative. And if the carbon is more electronegative, the carbon CH bond, the CH bond, the electron will go to the carbon more, and the H will be more like a H+, right? And another way to think about this is that how do we judge the acidity of a compound? Still remember? So we can judge from the stability of the conjugate base. So the more stable conjugate base means more acidic proton, okay? And because this acetylene has more S character, it's closer to the nuclei, so it's more stable. That means the C minus is more stable. The C more stable than the CH3 minus or than this alkynyl minus. This is the most stable conjugate base. That means the CH bond is the more acidic CH bond. Okay, so that's why alkyne has a a much higher acidity than the alkene and the alkane. Okay, and because of this more acidity of the CH bond of alkynes, we can have new reactions that only alkyne can have. Okay, it can be deprotonated. And I think in the Friday's lecture, I will show you the strong acidity of the CH bond here can facilitate the deprotonation. And the deprotonation species like the acetylide anion can react with some electrophiles like this CH3CH2Br to form the new CC bond. And this is a particularly important reaction because it can form a longer chain of the carbon, right? From the alkyne, the terminal can be linked to another chain of carbon. And this is very useful in a lot of synthesis. And we'll talk about some complex molecule synthesis next time using this kind of acidity of the alkyne and the generated acetylide anions by base. Okay, so I think this Friday, we will finish the chapter 7, and we will discuss some of the synthesis of target molecule that's going to be touched briefly in midterm 1. And for the next Monday, I think we will do a review section on all the things we have learned from chapter 1 to 7. And the next Friday, the Friday of next week, is the midterm 1. Okay, so we have full lectures next Tuesday, 2 double lectures to review all the things we have learned and do some practice. Okay, I hope that will better prepare you for the midterm 1 next Friday. All right, so you guys really need to catch up with the lectures and don't wait until the last moment to start to reviewing all these stuff and start to do the practice problems on the Moodle. All right, so I will see you this Friday.